Okay, so imagine you're holding a piece of paper with a messy handwritten number on it, maybe a slightly smudged 3.
Mm-hmm.
Your brain figures out it's a 3-pack instantly, effortlessly.
Yeah.
But now, try programming a computer to do that, pixel by pixel.
Oh, yeah.
You'd have to write code for every possible angle, every thickness, every little variation.
Yeah.
It gets incredibly complicated, kind of, well, comical.
It really does. Traditional programming struggles with that kind of fuzzy, flexible pattern recognition. It just doesn't quite fit the model.
And that challenge is exactly where the idea of a neural network starts to look really promising, isn't it?
Exactly. It offers a different way in.
Which is perfect, because that's our mission today, to take a deep dive into what a simple neural network is, specifically its structure.
Right.
We're looking at it not as, some futuristic buzzword, but as a fascinating piece of math, using that classic task of recognizing handwritten digits as our guide.
Yeah, and we've been unpacking some great source material that lays out this foundational structure step by step. Think of this as understanding the building blocks before you can even begin to talk about how these networks actually learn to do things like recognize digits. It's fundamental.
Right, you absolutely need to know how it's put together first.
Yeah.
Makes sense. Now, the name neural network gets thrown around, and yes, it's loosely inspired by biological brains.
It is, yeah.
But the sources we've looked at are pretty clear. Don't get too stuck on the biological analogy. The key is really the structure.
Definitely. That structure is built from these fundamental units that, in this context, we simply call neurons.
Okay. Neurons.
Forget the biology for a moment here. A neuron is just something that holds a single number. That's it.
A number between 0 and 1? Is that right?
Exactly. 0 and 1. And that number is the neuron's activation.
Activation.
A higher number means that neuron is more active or lit up for whatever it's supposed to represent. Closer to 1, more active. Closer to 0, less so.
Okay, so you have these simple units just holding a number between 0 and 1. And they aren't just scattered randomly. The first really crucial piece of the structure is that they're organized into layers.
That's the fundamental architecture. Absolutely key. Using our digit recognition example, you typically see 3 main types of layers.
Starting with the input layer. So if you're feeding the network an image, like say a 28 by 28 pixel picture of a digit, you have one neuron in this first layer for every single pixel.
Which in that case means 784 neurons just for the input layer. A lot of them.
Wow, okay.
And the activation of each of those neurons is simply the grayscale value of its corresponding pixel. Think 0 for black, 1 for white, and, shades in between.
Okay, so the image itself just becomes this pattern of numbers of activations in this first layer.
Precisely.
And you skip to the very end, the output layer.
For recognizing digits 0 through 9, the output layer has 10 neurons.
1 for each digit.
1 for each possible digit. 0, 1, 2, all the way up to 9.
And the idea is that after all the processing happens, the activation levels of these 10 neurons tell you what the network thinks the digit is.
That's the goal. Ideally, the neuron corresponding to the correct digit, say the 3 neuron, if the image was a 3-Han, will have the highest activation, something close to 1.
And the others?
While the others hopefully stay low, closer to 0, the network's guess is simply whichever output neuron is most lit up. The highest activation wins.
Input, output, and then the layers in between, the hidden layers. This is where things get interesting and maybe initially a bit mysterious.
The giant question mark layers, as the source material playfully calls them. Yeah.
Okay.
In the simple network example we're using, there are 2 hidden layers, and each one contains 16 neurons.
16 each. Okay. And the number of layers, like 2 here, and the number of neurons per layer, 16, that isn't some fixed law of nature, right? It sounds like you might choose those numbers somewhat arbitrarily, or maybe just figure out what works best through trial and error.
That's a really important point, yes. While there are principles and common practices that guide those choices, there's a lot of flexibility. And quite a bit of experimentation often involved in deciding the exact architecture of those hidden layers. It's part of the design process.
But the core flow is always the same. Activations from one layer feed into and determine the activations of the next layer. Is that right?
Exactly. Information flows sequentially through the network, layer by layer. Input affects the first hidden affects the second hidden affects the output.
So what's the underlying idea here? I mean, why build it this way? What are the hidden layers supposed to be doing with this cascading information?
This is where the layered structure starts to feel really powerful. The fundamental hope, and it is a hope initially, and the guiding principle is that these hidden layers learn to detect increasingly complex patterns. They build up a hierarchy of features from the simple input data.
Like starting simple and getting more complex as you go deeper into the network.
Yes, exactly. For the digit recognition, you'd hope the neurons in the first hidden layer, that's a second layer overall, remember, learn to pick out very basic features,
Like what?
like small edges or curves or corners, but in specific locations within the image. Very localized stuff.
Okay, so certain neurons in that second layer might light up only if there's a little horizontal line segment right here or a tiny curve over there.
Exactly. Simple geometric components. Then the hope is that the neurons in the second hidden layer, the third layer overall, take those simple edge detections and combine them.
Combine them how?
Well, maybe a neuron in this layer lights up if it sees multiple edges arranged in a way that forms a loop. Or maybe another one recognizes a long vertical line or a diagonal slash by seeing combinations of smaller edge detectors active in the previous layer.
Ah, I see. So the third layer isn't looking for raw edges anymore. It's looking for combinations of edges, the building blocks of shapes, like
Mhm.
loops and lines.
Precisely. It's a step up in abstraction.
Hmm.
And finally, the output layer neurons, the ones for 0 through 9, they look at the pattern of activation in that last hidden layer, the one detecting loops and lines and such.
Okay.
A neuron for 9, for instance, might get a strong signal if the top loop neuron and the right vertical line neuron in the previous layer are both highly active.
Right. So the output layer isn't trying to directly recognize a 9 from a mess of pixels, which is super hard. It's recognizing it from these higher level features like loops and lines that the hidden layers have, well, hopefully learned to identify. That seems like a much more manageable task.
It is. It's decomposing the problem into these simpler hierarchical steps. And this isn't just for images.
Oh,
Think about speech recognition. The network might learn to detect fundamental frequencies in the first layer, combine them into phone or basic sounds in the next, combine those into syllables and then words. It's a really powerful pattern of abstraction that applies in many domains.
that hierarchical idea makes a lot of intuitive sense. Okay, but let's get down to the mechanism. How does the pattern of activation in one layer actually determine the pattern in the next? What's the actual math happening between the layers?
Right. This is the absolute core of how information flows. For any single neuron in a layer, let's say, a neuron in the first hidden layer, its activation is calculated based on every single neuron in the previous layer.
Every single one. Wow. Okay, how does it combine the signals from all those previous neurons? There were 784 in the input layer, right?
Yep, 784 inputs feeding into each of the 16 neurons in the first hidden layer. It does it through a weighted sum.
Weighted sum. Okay.
There's a number, a weight, assigned to every single connection between a neuron in the previous layer and the neuron we're currently focused on. So 784 weights leading into each neuron in that first hidden layer.
Weights. So they signify how much influence this previous neuron's activation has on this current neuron, like how strong the connection is.
Exactly. You take the activation of each neuron in the previous layer, multiply it by the weight on the connection going to the current neuron, and then you just add up all those results. All 784 of them in this case.
Okay.
Think of it like this. If you want a neuron to detect, say, a specific vertical edge in the middle of the image, you might assign large positive weights to the connections coming from the pixels that would form that edge.
Right.
And maybe you assign large negative weights to the connections from the pixels right next to it, the background.
Ah, so if the edge is there, the positive weights times the high activations give a big positive number, and the negative weights times low activations don't subtract much.
Or maybe the negative weights times high activations from background pixels actively reduce the sum if the edge isn't sharp. Either way, when the edge pattern is present, those weights ensure you get a big weighted sum.
Okay, so the weighted sum is kind of like a measure of how well the pattern of activation in the previous layer matches the pattern encoded by this neuron's specific set of incoming weights.
Yes, that's a great way to put it. It's like pattern matching. But there's one more crucial piece before we get the final activation number, a bias.
A bias. What's that doing? Another number.
It's just a single number, yeah, added onto that weighted sum for each neuron. Think of it as an extra nudge, or maybe like a threshold.
A threshold.
Yeah, it sort of determines how high the weighted sum needs to be before the neuron really starts to get active. A high bias makes it easier to activate. A low or very negative bias makes it harder. The total input signal to the neuron is actually the weighted sum plus this bias term.
Got it. weighted sum plus bias.
Yeah.
But hang on, that number could still be anything, right? Positive, negative, huge, tiny. And you said neuron activations have to live between 0 and 1. How do we get from potentially any number down to that specific 0, 1 range?
Excellent question. That's the job of the activation function. The sources we're using initially describe the sigmoid function. You might also hear it called the logistic function.
The one that squishes the numbers? I've
Yeah.
heard of that.
Precisely. That's a great description. You take that total input, the weighted sum, plus the bias, and you pass it through the sigmoid function.
And what does it do?
It takes any input number, no matter how large or small, positive or negative, and it maps it smoothly into the range strictly between 0 and 1. Very negative inputs get mapped very close to 0. Very positive inputs get mapped very close to 1.
And inputs around 0?
They map somewhere in the middle, maybe around 0.5, and it transitions smoothly between those extremes. It's an S-shaped curve.
Okay, so let me recap this step because it feels important. For every neuron in a layer, that isn't the input layer, you calculate its activation like this. You look back at all the activations in the previous layer.
Yep.
You multiply each of those previous activations by its unique connection weight leading to this neuron. You sum all those products up. You add this neuron's unique bias.
Mm-hmm.
And then you feed that final total number into an activation function like sigmoid to get this neuron's final activation value, which will be between 0 and 1.
You've absolutely got it. That's the core calculation. And remember, every neuron in the layer does the same type of calculation, but each one uses its own unique set of incoming weights and its own unique bias. That's what makes them specialized.
Okay, so let me see if I'm connecting the dots here then. The entire neural network, from those 784 pixel values hitting the input layer all the way through the hidden layers to the 10 probability numbers coming out of the output layer. Can you see that whole thing as just one massive, complex mathematical function?
It absolutely is. Fundamentally, that's what it is. It's a function that takes an array of 784 numbers as input and transforms them through all these layers of weighted sums, biases, and activation functions into an array of 10 numbers as output.
And the things that define this specific, very complex function, the adjustable parts, the
Yeah.
knobs and dials, if you will, are all those thousands of weights and biases.
Precisely. They are the network's parameters. They are what you can change to alter the function's behavior. And even in our relatively simple example network, 784 inputs, 2 hidden layers of 16 neurons each, 10 outputs, the number of these parameters is already significant.
How many are we actually talking about? Did the sources quantify that?
They did. Let's think. From the input layer, 784 neurons, to the first hidden layer, 16 neurons, that's 784 times 16 weights.
Okay, that's over 12,000 already.
Plus 16 biases, one for each neuron in that hidden layer. Then from the first hidden layer to the second hidden layer, both have 16 neurons, so that's 16 times 16 weights,
256.
plus another 16 biases. And finally, from the second hidden layer, 16 neurons, to the output layer, 10 neurons. That's 16 times 10 weights,
160.
plus the final 10 biases for the output neurons.
Okay, so 12,544 plus 16 plus 256 plus 16 plus 160 plus 10. The source material notes it adds up to nearly 13,000 total weights and biases.
13,000 adjustable numbers, give or take. Even in this pretty basic setup. And this is a key insight, right? It shows the sheer complexity and flexibility that this structure provides.
Whoa! 13,000 different knobs you can turn to change how this massive function behaves. And I guess this is the critical link then. When we say a neural network is learning, what we really mean is the computer is somehow figuring out the right values for those nearly 13,000 weights and biases so that the network, this big function, actually performs the task we want, like correctly identifying handwritten digits.
That's the essence of it. Learning is finding the optimal, or at least a good set of settings for all those parameters. And the structure we've just described provides the framework, the potential for building that incredibly complex, adaptable function.
And thinking about what those weights and biases might represent, maybe the weights coming into a specific neuron encode the pattern for an edge.
Yeah.
And its bias adjusts its sensitivity. It starts to feel a little less like a complete black box. It helps understand why the structure is designed this way, and maybe gives you hints if things aren't working as expected during training.
It provides that conceptual bridge, between the raw math and the higher level task we're trying to achieve.
Okay, so we've covered the layers, the neurons, how activation flows via weights, biases, and that sigmoid activation function. But I noticed the material included a little postscript or update about activation functions. Something else is used now.
Ah, yes, a very important practical evolution. While the sigmoid function was important historically and partly popular because that 0 to 1 range felt kind of analogous to biological neurons firing or not.
Right, the biological inspiration again.
Exactly. But many modern networks, maybe even most, often use a different activation function called ReLU.
ReLU. ReLU, that sounds very technical.
It stands for Rectified Linear Unit, and ironically, despite the fancy name, it's mathematically much simpler than sigmoid.
Simpler, really.
All it does is take the maximum 0 and the input signal, that's the weighted sum plus bias. So if the input signal is positive, ReLU just outputs that input value itself unchanged.
Huh.
If the input signal is 0 or negative, ReLU just outputs 0.
Wait, that's it? It's just max? 0 input? So it's 0 if the input's negative, and it's just the input number itself if it's positive?
Yeah.
Yeah, that is way simpler than the sigmoid curve.
It is. And the source notes that despite sigmoid's neat 0 to 1 range, ReLU is often found to be easier and faster to train in practice for deep networks. It avoids certain problems that can occur with sigmoid during the learning process.
Interesting.
It's a good example of how the field evolves based on what works best empirically, in the real world, sometimes diverging from the original biological inspiration.
Fascinating. Okay, so just to wrap up the structural piece then, make sure we got it.
Yeah.
We've got neurons holding activation values, usually between 0 and 1 conceptually.
Mm-hmm.
They're organized in layers,
Mm-hmm.
input, hidden layers, output layer.
Mm-hmm.
Information flows from one layer to the next. The connection strength is determined by weights.
Yes.
Each neuron also has a bias added to its weighted input.
Correct.
And that total signal, weighted sum plus bias, gets passed through an activation function, like the classic sigmoid or the more modern ReLU, to produce the neuron's final activation output.
You've nailed it. And this layered architecture, powered by all those adjustable weights and biases, transforms the initial input data.
With the hope and the design principle that the hidden layers learn to build up those hierarchical feature detection's edges to loops to digits, for example, leading finally to the output layer's prediction.
That's the fundamental structure and how information moves through it, absolutely.
So there we have it. We've taken a deep dive into the fundamental structure of a simple neural network, really understanding the components, how they're organized, and the mathematical mechanism that allows information to flow and be transformed through them.
And seeing that structure, understanding those pieces, is the essential groundwork. But, as you mentioned earlier, the true power, maybe the magic, comes from the learning process.
Right.
How does the network automatically find the best values for those thousands or even millions in bigger networks of weights and biases to actually perform a task well? That's a whole other fascinating story for another deep dive.
It really is.
Mm-hmm.
But just sitting with what we have covered today,
Yeah.
think about it. Nearly 13,000 parameters, weights, and biases in even this simple digit-recognizing network.
Yeah, it's a lot.
If learning is essentially just the process of setting those thousands of tiny knobs and dials to create this complex function that can somehow magically recognize a messy 3,
Yeah.
what does that tell you about the sheer complexity and flexibility that this structure allows for? And how much of the network's eventual capability, its intelligence maybe, comes simply from having that incredibly vast space of possible configurations, possible functions to explore during training? It's kind of mind-bending when you think about it that way, isn't it?
It really is. The potential is enormous, just baked into the structure itself.
Something definitely worth mulling over.